Everyone to this to this first session of the European Non-Associative Algebra seminar to be held online each Monday. Now, of course, it's nice to meet colleagues face to face, but with funding for travel becoming more difficult to obtain, I think that initiatives such as this are valuable, and I'd like to thank the organisers for arranging it. Well, it's appropriate that this first talk should be given by such a distinguished non-associative algebraist as my longtime friend, Alberto Elduque. Notice I didn't say old friend, Alberto.
I noticed that.
And I think once Alberto starts talking, it might be helpful if everybody mutes their microphones to cut out any other background noise. So today, Alberto is going to talk to us about tensor categories, algebras, and superalgebras. So over to you, Alberto.
Thank you very much, David, for a very nice introduction. And let me start thanking the organizers of this seminar, European seminar, for this opportunity to talk about the things I've been doing lately. And so what I'm going to talk about today is based on joint work with my student, Alberto Garcia, and with Umud Sajim. And we have been working for some months on this. And it is a way to go from algebras to superalgebras, at least over fields of characteristic 3. And most of the last part of the talk will be about the characteristic 3, because it presents some special features. But let me start with the origin, at least for me, of all this. And this is something I did years ago, where I was dealing with symplectic triple systems. And what are these symplectic triple systems? Every time you have a Lie algebra that contains a subalgebra isomorphic to SL2, and such that as a module for SL2, it consists of the adjoint module of a number of copies of the natural module, which is the two-dimensional natural module for SL2, and a number of copies of the trivial module for SL2. Well, the sum of the copies of the trivial module is the centralizer of our subalgebra SL2, so it is also a subalgebra. So our Lie algebra splits in this way, and this gives a gradient over the integers modulo 2. And this subspace that appears here, that counts the number of copies of the natural module, the natural two-dimensional module for SL2 that appear there, becomes a symplectic triple system. Actually, whenever you have a Lie algebra which is set to graded, and in the even part you have a copy of SL2 plus the centralizer, and the odd part is module, which is the tensor product of the natural module for SL2 and another module for D, then necessarily the bracket of two basic odd elements, say U tensor X, V tensor Y, where U and V are in the natural module, two-dimensional module for SL2, and X and Y are in T. Well, it turns out that there is a unique SL2 invariant bilinear 4 defined on the natural two-dimensional module. And this is going to be denoted like this, and this is skew symmetric. And up to scalars, there is just one. And there is only one SL2 invariant bilinear map from the Cartesian product of two copies of the natural two-dimensional module onto SL2. And this is given by this gamma UV, which is the formula appears here at the bottom. And because of this uniqueness of these SL2 invariant maps, the bracket of two odd elements is necessarily of this form that appears here, where first we have a bilinear skew symmetric 4 defined on T, And here we have a map from T cross T into D. Okay, and this is symmetric. And then with this symmetric map, one can define a triple product in T, and T becomes a symplectic triple system. Anyway, the algebras that contain subalgebra isomorphic to SL2 with these properties, that only one copy of the joint module, several copies of the two-dimensional natural module, and several copies of the trivial module for SL2 appeared, all have a bracket determined in this way. And some years ago, I realized that only in characteristic 3, one can play a trick here. And the trick is, okay, forget about SL2 here, and forget about the natural two-dimensional model. Okay, so just forget about that and just keep D and T. And give a bracket, well, D is a Lie subalgebra, T is a module for D, so we can define naturally a bracket here, and we can define also a bracket for elements in T using the map that had appeared earlier, this one. Okay, so see, instead of considering the whole Lie algebra, I erase SL2 and I erase the two-dimensional module, and I just keep D and T and keep the brackets that appear there. And with this, D plus T becomes a Lie superalgebra. And this is something that appears only in characteristic 3. And using this, I was able to define a new family of simple contragradient Lie superalgebras that were specific of characteristic 3 and were unknown at that point. Okay, so that was quite interesting because all of a sudden I was able to define 5 new simple Lie superalgebras specific of characteristic 3, just playing with this silly question. Okay, but then very recently, Arun Kannan considered a much more general approach to go from Lie algebras to Lie superalgebras that works mainly in characteristic 3. So his idea was to consider exceptional simple Lie algebras endowed with an nilpotent derivation of degree at most 3. Okay, and once we have such a nilpotent derivation, well, we can decompose our Lie algebra, or exceptional simple Lie algebra, according to the Jordan blocks that appear related to this nilpotent endomorphism, linear endomorphism, or our Lie algebra. And see, in the situation that I have considered so far, one can take as D the adjoint action of this element in SL2. And this is an nilpotent derivation satisfying this property. So one can do that. And this nilpotent derivation allows to view the Lie algebra we are considering, the exceptional simple Lie algebra, as an algebra in the category of representations of the Frobenius kernel in characteristic 3. This is the affine group scheme, such that on objects takes R to the set of nilpotent elements of degree at most 3 in R. And so this is an affine, nice affine group scheme in characteristic 3. And the Hopf algebra that represents this affine group scheme is just the polynomial algebra in one variable, mod out by the ideal generated by the variable cube, x cube, ideal generated by x cube. So, and the action of the variable x is given by the action of the nilpotent derivation. I will come back to this later on. And so, once he considered the exceptional simple Lie algebras as algebras in this category, of representations of this Frobenius kernel, he considered the so-called semi-simplification of this category. This is a symmetric tensor category. I will review all these things later on. So one can go through the so-called semi-simplification of this category. And the semi-simplification of this category is the so-called Berlin category in characteristic 3. And this is the category up to equivalence. This is the category of vector superspaces. And then an algebra in the category of vector superspaces is superalgebra. So in this way, the semi-simplification process of the category of the representation of the Frobenius kernel gives a way to go from Lie algebras to Lie superalgebras in characteristic 3. He was able to do a few things also in other finite characteristics, but the situation is more important. In characteristic 3, the situation is very clean and very straightforward. Okay, so my idea is to review what actually, when I started to look at this, I barely knew the definition of a tensor category or a symmetric tensor category. I had no idea about this, what the semi-simplification of a symmetric tensor category is, what does this means. And so I had to study together with Alberto and Umut. We started to study all these things to understand what Aaron Cannon had done, and to even look at these things in a different way and being able to produce some new objects too. Okay, so this is the idea of the talk: to review the definition of symmetric tensor categories, to review the definition of semi-simplification of such a category, and then to explain how this in characteristic 3 allows to go from algebras to superalgebras, starting with either the same category that Aaron Cannon considered, which is the representations of this Frobenius kernel, or we consider another not exactly equivalent way of doing this, which was considering the representation of the cyclic group of order 3, the category of representations of the cyclic group of order 3. And this allows to go from algebras to superalgebras. And in particular, in the last part, we'll look at octonions. Octonions in characteristic 3. Well, the algebra of split octonions can be considered as an algebra in the category of representation of the cyclic group of order 3. So one can apply this process, and what one gets are precisely the known composition superalgebras. These are classified, and we get all the exceptional composition superalgebras that appear, unital composition superalgebras. So this is the idea. So let's start with the review of the definitions of the symmetric tensor categories. So first, we need to review what a monoidal category is about. And a monoidal category is just a category with a B-functor, which is, you should think of finite dimensional vector spaces with a tensor product. This is the example you should keep in mind. So we have a category with such a tensor product, and this must satisfy some properties. The first one, there should be a unit object, which in the case of vector spaces is just the one-dimensional vector space, if you want the ground field. And whenever we tensor with the ground field, we get something isomorphic to the original vector space we started with. So we have this property here. And the tensor product is associative up to natural isomorphism. And there must be some natural coherence conditions for this natural isomorphism with the unitors and associators, but these are very natural. So whenever we take 4 different objects, we can associate in several ways, and we have several isomorphisms that relate these different ways of putting parentheses, and all should be coherent. Okay, so these are the natural things. So this is quite natural. and then once we have monoidal categories, we need to get the functors among these categories. So a functor between 2 monoidal categories is called a monoidal functor if it preserves the unit object up to an isomorphism, and the image of the tensor product should be isomorphic to the tensor product of the images of 2 objects. Okay, but this should be natural. So there, must be natural isomorphisms J, X, Y in this way. Okay, so this is quite natural. Once we define monoidal categories, the definition of monoidal functors. Now, we need also a braiding, and probably you're more familiar with that. A braiding is just a natural isomorphism from X tensor Y to Y tensor X that must satisfy some natural compatibility conditions with unit objects and the associators. These are quite natural. And in case this braiding satisfies this involutive condition, we talk about a symmetric monoidal category. If the monoidal category is not symmetric, then for each object X, we can take tensor products of the same object, and then we have a representation of the braid group. If the category is symmetric, then we have a representation of the symmetric group here, and this appears in many places. So more definitions that we need is the definition of rigid symmetric monoidal category. And this is the existence of duals with the natural maps, the natural properties of duals in the category of finite dimensional vector spaces. So once we have a dual object, we should have an evaluation morphism from X dual tensor X into the unit object, which for vector spaces is just the ground field, and a co-evaluation morphism that for vector spaces is obtained by considering a basis in our vector space and the dual basis in the dual vector space. And this doesn't depend on the dual basis that we consider. And this evaluation and co-evaluation must satisfy the natural properties satisfied by the natural evaluation and co-evaluation maps for finite dimensional vector spaces. So once we start with an object X, we co-evaluate on the left. So we go from X to X tensor X star, and then X, and then we can evaluate on the right, go to X again, because I'm forgetting about unitors, and this should be the identity. And similarly, we start with the dual object. So rigid symmetric monoidal categories have a tensor product with the natural properties, symmetric braiding, and also dual objects. Okay, so these are the definitions. And finally, a symmetric tensor category over a field F is a rigid symmetric monoidal category. So all the things we have considered so far, with the following extra properties. It has to be an abelian category, and more than that, actually. So the spaces, the abelian groups of homomorphisms should be actually vector spaces over F. The tensor product should be bilinear. And this category must be also locally finite. So this means that the objects must have finite length, and the spaces of morphisms should be finite dimensional. And finally, the unit object, the vector space of endomorphisms of the unit object should be just one dimensional, and therefore spanned by the identity morphism of the unit object. So this is a symmetric tensor category. And examples, well, I was telling you, this is the main example. One should keep in mind the category of finite dimensional vector spaces over any field F, or the category of finite dimensional representations for a triangular Hopf algebra, or the category of representations of finite dimensional representations of any affine group scheme, which, well, this category is autoequivalence, natural equivalence, the category of co-representations, co-modules for the commutative Hopf algebra that represents the affine group scheme, G. So one can consider this in different ways. Or the category of finite dimensional vector superspaces. So these are just set to graded vector spaces, and the morphism should preserve the grading over the integers modulo 2. Okay, and the braiding here or here is given just by the natural morphism that swaps the order of the elements. It goes from X tensor Y to Y tensor X. Here, all the elements are vector spaces. The tensor product is the natural tensor product for the vector spaces, and we have the natural swap map. And for finite dimensional vector superspaces, we have the parity swap. So whenever we switch to odd elements, we must add a minus sign there to get the braiding in this category. But with these usual braidings and tensor products and everything, all these are examples of these categories, of symmetric tensor categories. Now, in any of these categories, we can consider algebras. Well, an algebra in the category of vector spaces is just a vector space with a bilinear multiplication. Well, an algebra in a symmetric tensor category is an object endowed with a morphism that goes from A tensor A into A. And this is the natural definition. And then we can define commutative algebras in a symmetric tensor category. The commutativity is given by the braiding. So this map equals the map composed with the braiding. The braiding, you should think of the braiding as changing the order, the extension of this natural swap. Associative, yes, it's same properties. Lie, well, we may have some problems in characteristic 2 or 3, but in principle, the characteristic, characteristic 3, there are problems for Lie superalgebras. For Lie algebras, just in characteristic 2. In characteristic 2, anticommutativity is not defined in this way, in general. But well, when dealing with general symmetric tensor categories, we just extend the linearizations of the anticommutativity property, and the linearization is just that the bracket of xy is minus the bracket of yx. So the natural extension to any symmetric tensor category is this formula. And then this is the analogous, well, this is the extension of Jacobi identity that is valid for any symmetric tensor category. So we can define Lie algebras in any symmetric tensor category. We can define Jordan algebras. We just have to linearize first the Jordan identity and the commutativity, and then express all this in terms of the swap morphism, and substitute the swap morphism by the corresponding braiding in the category, and that's it. So we can define all kind of algebras in symmetric tensor categories. In particular, Lie algebras, Jordan algebras. Well, there are some subtle questions in low characteristics, but for most situations, we are safe by just taking the linearization of the identities that define a variety and then substituting the swap morphism by the corresponding braid. Okay, so this is a review of the symmetric tensor categories. And just remark that superalgebras are just algebras in the symmetric tensor category of finite dimensional supervector spaces, because I will deal just with finite dimensional algebras. So what about the semi-simplification? Well, this is quite interesting, and to define the semi-simplification of a symmetric tensor category, we have to define first the trace and the dimension of an object in a symmetric tensor category. So if we start with a symmetric tensor category, C, and we take an endomorphism of an object X in this symmetric tensor category, the trace is defined as follows. We start with a unit object. For vector spaces, this is just the ground field, or for vector superspaces, this is just the ground field. We co-evaluate, so go to X tensor X dual, apply F in the first place, the first slot, then apply the braiding, so we swap the order, and then we evaluate. And if you look at what this means in the category of vector spaces, finite dimensional vector spaces, this is the ground field F, this is the ground field F. In the middle, you co-evaluate with respect to the vector space you are considering, X, apply F, and in order to co-evaluate, you have to take dual basis in X and X star, and then take the evaluation, and what you get is the usual trace. When you compose all these morphisms, you get the usual trace of the endomorphism F. So it has a natural, once you are able to express something that is valid for vector spaces in terms just of the braiding of the category of vector spaces and the tensor product and the unitor and so on, you can extend all this to any symmetric tensor category. And this is what happens here. So we can extend the trace to any symmetric tensor category. And in particular, we can extend the notion of dimension. So the dimension is just the trace of the identity morphism. Okay? So this is a natural extension of what happens for vector spaces. And once we define the trace and the dimension, we have to define, well, we have to label some homomorphism as being negligible. Okay, so morphism in asymmetric tensor category from X to Y is said to be negligible if the trace of the composition, say on the right with any morphism in the reverse order, is always zero. It doesn't matter whether you put the G on the right or on the left, the same thing, the same family of negligible homomorphisms, although the proof is natural, but it's not that, it's a nice exercise when one starts looking at this kind of things, this kind of stuff. Okay, and then given any two objects, X and Y, we can consider the negligible homomorphism, the negligible morphism in the category from X to Y, and this for a subspace of the space of morphisms from X to Y. And it is more than that, because when we compose any negligible morphism with any other morphism, then we get a negligible morphism. So whenever we multiply negligible morphism by arbitrary morphism, we get negligible morphisms. So we say that these subspaces form a tensor ideal. And once we have this tensor ideal, we can define a new category. And this is the semi-simplification of our symmetric tensor category. So the new category, the objects of the new category are the same objects. So objects are exactly the same. What we do to define the new category is to define new morphisms. And the morphism, the new morphisms are just the classes of the old morphism modulo negligible morphism. Okay, so what we are changing are the morphisms, not the objects of the category. And this new category is called the semi-simplification. And it inherits the tensor product from the category. It inherits the unit object and the dual objects and all kinds of things that we already have. So we get another symmetric tensor category. And of course, we have a natural functor from our category, our original category, to its semi-simplification, that it is the identity on objects, because objects are the same. And it takes any morphism in C to the corresponding morphism, the class of this morphism, modulo negligible morphism. So it goes from, it takes any morphism to the class of this morphism, modulo negligible morphism. And this preserves the gradient, the tensor product, the F-linear character. So this is a nice functor preserving all the things that we have here involved. Okay, so this is the semi-simplification. Again, objects are the same. What we change are the morphisms. And the interesting thing is that this new category is semi-simple in the sense that any object is a direct sum of finitely many simple objects. Okay? And this is the interesting thing. Actually, the simple objects in the semi-simple category correspond to the indecomposable objects in the former category, in the original category of non-zero dimension. Because it may well happen that non-zero objects in our original category have 0 dimension. And then in the new category, they become, up to isomorphism, the 0 object in the new linear category, in particular abelian category. And we'll come to the examples we are interested in a moment. So objects with dimension 0, with our definition of dimension using the trace, become, up to isomorphism, the 0 object in the new category, in the semi-simplified category. Okay, so this is the semi-simple categories. And in particular, if we start with a field of characteristic prime characteristic P, and we consider the finite dimensional representations of the cyclic group of order P, this for a category, the category of representation of CP, or if up to natural equivalence, this is the category of the finite dimensional representations of the corresponding constant affine group scheme. And this is, whenever we have an object here, well, an object here is a vector space, a finite dimensional vector space with an axiom of the cyclic group of order P. But once you take a generator of the cyclic group of order P, it is enough to give the axiom of this element. And this generator acts as a linear automorphism of order P. Okay, but we are in characteristic P. So if you have a linear automorphism of order P, if you subtract the identity, you get a nilpotent endomorphism with nilpotent degree at most P. Okay, so actually the objects in this category are vector spaces with an nilpotent endomorphism of nilpotent degree at most P. And therefore we can, we have, this is something we do with our linear algebra students. We have a vector space and a nilpotent endomorphism, and then we obtain the Jordan canonical form of this endomorphism. So what we do is we split the vector space into a direct sum of Jordan blocks, and each Jordan block corresponds to an indecomposable module in this category. But of course, the splitting into a direct sum of indecomposable is not unique, but but they are just indecomposable. But whenever we go to the semi-simplification of this category, these indecomposable objects either become isomorphic to the 0 object, or they become simple objects. They become irreducible objects in the new category. Well, the semi-simplification of this category is the so-called Berlinde category in characteristic P, and this is a symmetric tensor category. Okay. Actually, Berlinde category can be obtained also in terms of the Frobenius kernel I mentioned at the beginning of the talk. So it can be obtained in 2 ways, and sometimes it may be more interesting to obtain one way or another. So the semi-simplification, these categories, the category of the representation of the Frobenius kernel is not isomorphic to the category of representations of CP, the cyclic group, but the semi-simplifications are equivalent categories. Okay, so let's go from algebras to superalgebras using all this background of symmetric tensor categories. So I'm going to work just over phase of characteristic 3. So we fix ground field of characteristic 3 And I'm going to consider the category of finite dimensional representations of the cyclic group of order 3. Okay, so an object here is a vector space with a linear automorphism of order 3. Just that. So we fix a generator of our cyclic group, and then we have 3 different indecomposable objects corresponding to the Jordan blocks of length 1, 2, or 3. Okay, so the first, the one-dimensional indecomposable objects are up to isomorphism, the field with the trivial axiom of the cyclic group. The two-dimensional indecomposable objects are isomorphic to a two-dimensional vector space with this axiom of sigma of our generator. This corresponds to a Jordan block of length 2, and the same. The only up to isomorphism indecomposable object of length 3 is a three-dimensional vector space with this axiom of sigma that appears here. So it's just obtaining the Jordan block decomposition of a linear automorphism of order 3 in our vector space. So any object decomposes non-uniquely because Jordan blocks are not unique. We have the same number of Jordan blocks, the same lengths of the Jordan blocks, but the Jordan blocks themselves are not unique. So decomposes non-uniquely as a direct sum of copies of the one-dimensional indecomposable module or two-dimensional or three-dimensional indecomposable module. Okay, and this happens for any object. Now, properties. Now, remember, the semi-simplification of this category is the Berlinde category, and I will denote with an, when I put brackets around an morphism, I mean the class of this morphism modulo negligible morphism. Okay, so I'm looking at morphism in the semi-simplification, the semi-simplified category. And then, well, these Jordan blocks are simple in the new category. So the endomorphisms of these objects are just one-dimensional, actually are absolutely simple. But the Jordan block of length 3, the dimension, with our definition of dimension is 0, so it becomes isomorphic to the 0 object, and it means that the endomorphisms are just, well, we just have the 0 endomorphism, which means that all morphisms in our original category are negligible. So when we go to semi-simplification, all morphisms become the 0 morphism. Okay, the negligible morphism fill completely the subspace of morphism. And these are different simple objects, so the morphism between different simple objects are 0. So we have all these properties that we know more in general, but in particular for this symmetric tensor category and its semi-simplification. And now, with respect to the tensor product, well, we have natural situations that the V0 is actually the field, which is the unit object. So these are isomorphic to VI, the same here. But in our original category, V1 tensor V1 is isomorphic to V0 plus V2. But V2 is 0 in the semi-simplified category. So in the semi-simplified category, in the Berlinde category, V1 tensor V1 is just isomorphic to V0. And the braiding behaves in a very natural way. The braiding in the new category, in the semi-simplified category, is given by considering the classes of the braidings in the original category. And the braiding in our original category is just the natural swap or tensor products. And whenever we perform the natural identifications, the only problem is when we swap odd elements. Well, when we swap the simple object different from the unit object, what we get is minus the identity. But this is quite natural when one performs, when one writes down the details of what we are doing. Okay, so this is what happens, and this implies that the Berlin category, the semi-simplification of the category of representation of C3, is naturally equivalent with an equivalence that respects tensor products and gradients and everything with the category of finite dimensional super vector spaces. This category. And the functor, the monoidal functor that performs this equivalence is given in this way. So if we start with a vector superspace, so it is just a vector space which is graded over the integers modulo 2, so we have an even part and an odd part. The object in the corresponding object in the Berlin category is just a number of copies of V0, as many copies as indicated by the dimension of X0 bar. So here the action of sigma is trivial. And then a number of copies of the two-dimensional Jordan block. So the action of C3 is here, it's trivial on X0 bar. And in this part, we have an action just on V1. Okay? We fix everything in X1 bar. And in this way, we get an object, which is an object. See, the objects in the semi-simplification are the objects in the original category, which is the representation of C3. So here we have a vector space with an action of the cyclic group of order 3. And the action is trivial in this part, is trivial in X1 bar, and it is the action we know in V1. So globally, we have an action of C3 here. So we have an object, natural object in the category of representation of C3. And for morphisms is the most natural thing and trivial thing that we can think of. Okay. So, and this preserves tensor products and everything. One has to be careful with the tensor product of odd parts, purely odd parts, but this is a monoidal functor. But being a monoidal functor means it preserves the tensor product, and the preservation of the tensor product is given by natural isomorphisms, J, and this has to be defined. So one has to be careful with this kind of details, but I don't want you to pay much attention to the details. The only problem is when one considers odd elements. Because see, this J has to be a morphism from the tensor product of F of one object of this type, tensor with F of another object. So we have on the left, we have the tensor product of two objects of this form. And on the right, we have a different thing. So on the left, we have the tensor product of two elements of the 4 that we had in the previous slide. And on the right, we have the tensor product of superspaces, and then we apply F. So this is what happens. And so this is the even part of the tensor product of two superspaces, X and Y. And this is the odd part of the tensor product of the superspace. And then we apply F and get this V1. Okay, there are details here. So just, it's enough to know that one has to be a bit careful with the odd part when we consider two odd elements, and being careful with that. But apart from that, everything is quite natural. Okay. So now, if we start with an algebra in the category of representation of C3, well, an algebra in this category is just an object in this category, so a vector space with an action of the cyclic group of order 3, and multiplication, which is a morphism in this category. So it is invariant, so sigma must act as an automorphism of the algebra. So an algebra in this category is just an algebra with an automorphism of order 3. This is an algebra in this category. It's just an algebra with an automorphism of order 3. So now, if we have an algebra in this category, well, here the multiplication is a morphism in this category. Now I go to the semi-simplified category. The object is the same, A, and the morphism is the class of the original morphism modulo negligible morphism. And this is an algebra in the semi-simplified category, Berlinde category. But this Berlinde category is equivalent to the category of super vector spaces. So up to isomorphism, there is a unique algebra in the category of super vector spaces, and this is a superalgebra that corresponds to our original algebra in the Berlinde category. So we move from an algebra in the category of representation of the cyclic group of order 3. This is an algebra with an automorphism of order 3. From here, we pass to the Berlinde category. And now we apply that the Berlinde category is equivalent to the category of superalgebras. So an algebra, so the Berlinde category is equivalent to the category of finite dimensional vector superspaces, and an algebra in the category of finite dimensional vector superspaces is nothing else but a finite dimensional superalgebra. So starting with algebra in the original category, we end up with a superalgebra. And this is valid in characteristic 3 because this works, this semi-simplification in characteristic 3. Okay. And to obtain this superalgebra, well, it is enough to split our original algebra into the Jordan blocks of length 1. The Jordan blocks of length 2 is split in a natural way with the heads and the tails of the blocks, and the Jordan blocks of length 3. So in order to get the superalgebra, just take all Jordan blocks of length 1 and all heads of the Jordan blocks of length 2. And this gives you a vector space graded by the integers modulo 2. And just taking this, one applies this recipe. So again, A0 bar, the even part, is the subspace spanned by the Jordan blocks of length 1. And A1 bar is the subspace spanned by the heads of the Jordan blocks of length 2. And so we have a superspace, and we define a multiplication M using the projection of the original multiplication onto the corresponding component, with some special attention paid to the case where we multiply two odd elements. So just one has to take care about the situation in which we have two odd elements. But apart from that, it's just the natural projections. And this is the superalgebra that one gets. So we start with an algebra in the category of the representation of C3. So this is a finite dimensional algebra endowed with an automorphism of order 3. From there, we move to Berlinde category, and this is equivalent to the category of vector superspaces. So using this process, we go from an algebra with an automorphism of order 3 to a superalgebra with no automorphism involved, just a superalgebra. Okay. And this is the way to do that, just using this recipe. Well, what happens if the characteristic is not 3? Well, not everything is lost. Berlinde category is no longer equivalent to the category of super vector spaces, but the full subcategory of the Berlinde category is equivalent to the category of super vector spaces. And actually, at the same time I was able to define this new family of simple Lie superalgebras, I was able also to define a new simple Lie superalgebra in characteristic 5. This new simple Lie superalgebra can be obtained also using this process of semi-simplification. Arun Kanan was able to obtain also this simple Lie superalgebra, starting with a simple Lie algebra of type E8, Cannon used derivations instead of automorphism. So he started with E8, considered a particular derivation, nilpotent derivation of nilpotent degree 5 in this algebra. And this particular derivation has a nice splitting. The Jordan blocks that appear are just of dimension 1, 4, or 5. And then just using the Jordan blocks of dimension 1 and 4, he's able to go to a superalgebra, which is exactly the superalgebra I obtained many years ago. And also using derivations instead of automorphisms, Cannon obtained not just the ones simply superalgebra that I had obtained with symplectic triple systems, but also all the algebras that, together with my former student Isabel Cunha, obtained in a so-called extended Freudian magic square, which is specific of characteristic 3 because it uses composition algebras and composition superalgebras to define this Freudian magic square. So Cannon was able to obtain all these things, but without working with composition algebras or superalgebras, just working directly with exceptional simple Lie algebras, the Dinkin diagrams, a nice canonical basis with several relations, and using some appropriate nilpotent derivations of these algebras. And for each case, he has to consider different ad hoc defined nilpotent derivations. Okay, so let me show you finally that all this can be applied to octonions in characteristic 3. And if we had known about all this process, probably we would have discovered the composition superalgebras earlier than they were discovered. So, well, what are composition algebras? Without categories. Yes, composition algebras over a field. A composition algebra over a field is an algebra, so a vector space with a multiplication, mu, and a non-degenerate singular multiplicative quadratic form. So multiplicative means that the norm of the product is the product of the norms. So the norm of xy is the norm of x times the norm of y. Okay, this is a composition algebra. If composition algebra is unital, then these are also called Hurwitz algebras. Well, what we get, the unital composition algebras are the generalization to arbitrary fields of the classical real algebras, real division algebras of real numbers, complex numbers, quaternions, and octonions. The dimension is always 1, 2, 4, or 8 over arbitrary fields. If we forget about unital, if we consider more general composition algebras, then the dimension is still 1, 2, 4, 8, or infinity. There are infinite dimensional non-unital composition algebras. But if we impose the existence of a unit element, these are the possible dimensions that appear. And in dimension 8, the algebras that appear are the algebras that we know as Cayley algebras or octonion algebras in general. So assume that the characteristic is different from 2. If the characteristic is different from 2, we can linearize the multiplicative property of the norm. And then once we linearize the multiplicative property of the norm, well, we start linearizing the norm, which is a quadratic form. And when we linearize, what we get is a non-degenerate symmetric bilinear form. So in order to define a composition algebra in a symmetric tensor category, we need a product in this symmetric tensor category, so a morphism, this type, and a symmetric bilinear form, so a morphism of this type. The unit object in the symmetric tensor category plays the role of the field. And this norm has to be symmetric, so it has to work nicely with respect to the braiding. It has to be multiplicative, so first you have to linearize the multiplicative property for usual composition algebras. And once you have this property linearized, well, every time you have a swap of elements, you apply the braiding instead of the swap. And that's it. You get this property here. So this is the multiplicative property in symmetric tensor categories. And the non-degeneracy is also something that can be expressed in categorical terms. So we can extend the non-degeneracy condition in the bilinear form to any symmetric tensor category. So we can define compositional algebras in symmetric tensor categories. Now, we want to start with algebras in the category of representation of the cyclic group of order 3. So algebras in this category are just algebras with an automorphism of order 3. And it turns out that for Cayley algebras, the only Cayley algebras over a field of characteristic 3 that have an automorphism, an algebra automorphism of order 3, the only Cayley algebra is the split one. Division Cayley algebras over fields of characteristic 3 do not have automorphisms of order 3. So, and if it is a split, we have a canonical basis. So this is the multiplication table of the split Cayley algebra. A split means that the norm is isotropic. So there are non-zero elements with zero norm. Or in other words, it is not a division algebra. A Cayley algebra, which is not a division algebra, and there is only one up to isomorphism with two orthogonal primitive idempotents and the corresponding pairs components and a natural multiplication. And actually, any one of the two pairs components for these idempotents generate the whole algebra. Okay. So, and actually, we have exactly up to conjugation only 4 types of order 3 automorphisms. So we can look at the split Cayley algebra as an algebra in the category of representation of C3 only in 4 different types. And these are, well, this is just technical, but just these are this was described just a few years ago, because these automorphisms, these order 3 automorphisms, are important in order to describe idempotents in Okubo algebras. So what it was trying to do was to describe idempotents in Okubo algebras, and these automorphisms correspond to the so-called quaternionic idempotents in the split Okubo algebras, which there is only one. These correspond to the quadratic idempotents. The fourth one corresponds to the singular idempotents of the split Okubo algebra, and the third one corresponds to idempotents in the para-Cayley algebra. So this is why. Anyway, there are only 4 types. So with any of these automorphisms, we can think of C, of our Cayley algebra, as an algebra in the category of representation of the symmetric of the cyclic group of order 3. And then we can semi-simplify and move to superalgebras. And when we apply our recipe, what we get is, for the first type of automorphism, we get B42. For the second type, we do not get non-trivial superalgebras. The odd part becomes trivial, so it's just an algebra. And for the last 2 possible order 3 automorphisms, we get the composition superalgebra B12, which has dimension 3, B12 has dimension 3, and B42 has dimension 6. And these are the only exceptional unital composition superalgebras. These algebras were discovered by Sestakov when he was classifying prime alternative superalgebras and simple alternative superalgebras. And these are the only exceptional unital composition superalgebras. In other characteristics, any composition superalgebra has trivial odd part, with the exception of characteristic 3, with these 2 possibilities, and characteristic 2, where you can take a classical composition algebra with a gradient by the integers modulo 2. It becomes a superalgebra, but actually it is an algebra. So it is nothing new. The only new objects appear in characteristic 3. And this is what happens. Using this recipe, one can rediscover the composition superalgebras. So every time you have an algebra over a field of characteristic 3 with an automorphism of order 3, you can go through this process and see what kind of superalgebra appears. And there are chances that you get something new looking at that. Okay, so this is the message of the talk. Okay, this is the article I told you about Canon that started all this, and I trying to understand this beautiful paper. This is how we obtain these composition superalgebras from octonions and something else, because once we get composition superalgebras from octonions, one can semi-simplify the extended Freudenthal magic supersquare and get all the Lie superalgebras in this. So semi-simplifying the classical Freudenthal magic square, one gets the extended Freudenthal magic supersquare. Okay, and this is all I wanted to tell you about. Thank you very much for your attention.
Thank you, Alberto, for a very interesting and enjoyable talk. I have to say that in the early days of category theory, I just thought it was abstract nonsense. But as time's gone on, I've become increasingly aware of how foolish I was in that belief. Mm-hmm. So, does anyone have any questions for Alberto? You told us that Canon showed that you got a new superalgebra by using E8.
Yes.
Do you not get anything new with any of the other exceptional Lie algebras, or is that not known?
No, yeah. Actually, Canon uses F4, E6, E7, and E8.
Right.
G2 is too small, because when one semi-simplifies, one gets things that are even smaller. So G2 is too small. But in a way, if he does in a very combinatorial way using the linking diagram of F4, E6, E7, or E8, and so he starts with the linking diagram, natural canonical basis, corresponding split Lie algebra, and then finding a suitable nilpotent derivation. The question is that F4, E6, E7, and E8, the four of them can be constructed using Tits construction with an Cayley algebra and a Jordan algebra of degree 3, a simple Jordan algebra of degree 3. So if we start with a Cayley algebra and 3 by 3 Hermitian matrices over the field, or symmetric matrices over the field, then one gets F4. If one starts with a Cayley algebra and the algebra of 3 by 3 matrices considered as a Jordan algebra, one gets E6. And if one uses quaternions for the Jordan algebra, one gets E7, and if one uses octonions as the coordinate algebra of the Jordan algebra, one gets E8. So F4, E6, E7, and E8 can be constructed with Tits construction with a Cayley algebra and then a Jordan algebra. Then, well, Cayley algebra in characteristic 3 is endowed with an automorphism of order 3. So this means that the whole Tits construction, the whole Lie algebra, F4, E6, E7, or E8, is also endowed with a natural automorphism of order 3 that comes from the automorphism of order 3 in the Cayley algebra. So instead of doing what Canon did, one can use this, and then one gets simple Lie superalgebras in characteristic 3. Starting with F4, E6, E7, and E8, with an automorphism of order 3 that comes from this automorphism in the Cayley algebra, and then using the semi-simplification process, and one gets the Lie superalgebra. So not just E8. So actually, all the exceptional simple Lie algebras can be done, but it is quite open because in characteristic 3, there are more simple Lie algebras to deal with. And so one can, one starts with one of the, I don't remember the name, but well, in characteristic P, we have the classical simple Lie algebras, the Cartan type simple Lie algebras, but then in characteristic 3 or 5, we have some extra families of simple Lie algebras.
The Malikian algebras.
Yes, we have the Sklenin algebras, and there are some others algebras in characteristic 3. But anyway, this is something that can be considered. Take any of these simple Lie algebras, not just the classical E8, E7. Take any of these with either a nilpotent derivation of nilpotency degree at most 3 or an automorphism of order 3. And then one can apply these recipes and see what happens. Because some of the simple, in characteristic 3, we know the simple contragradient Lie superalgebras. But it may be well the case that we get something which is not contragradient. So, I mean, this is quite open. But it's not only for Lie algebras. Just start with any nice algebra over a field of characteristic 3 with an automorphism of order 3 or suitable nilpotent derivation, and one can apply this recipe and get a superalgebra. And well, we don't know much about simple algebras in many varieties in characteristic 3, superalgebras in many varieties. So this is a way of producing new objects and see if they fit into the known classifications. So that's why I was quite interested in showing this possibility, because probably in the audience there are people working in Lie algebra, but people working in Leibniz algebras or Jordan algebras or pre-Lie algebras or whatever.
Very interesting. Are there any more questions?
I have a question.
Yeah.
Alberto,
Yes.
so you consider mostly only in characteristic of the field of characteristic 3. But
Yes.
what about other prime characteristics? Is it more complicated or it's more simple?
No, it's more complicated. I mean, one can consider, for instance, think of characteristic 7, and you have an algebra with an automorphism of order 7. In characteristic 7. Then this is an algebra in the category of representation of the cyclic loop of order 7. And in characteristic 7, the semi-simplification of this category is the Verlinde category in characteristic 7. The problem is that the Verlinde category is not equivalent to the category of superalgebras. Sorry, it's not equivalent to the category of vector superspaces. So in this process, what you get is not a superalgebra. You get an algebra in a more complicated category. Anyway, it seems that Verlinde categories are quite important for people working in tensor categories, because they give examples of categories with dimensions which are not integers, and it is related to several conjectures in this. So another outcome of all this maybe that perhaps it is interesting to study algebras in categories different than just the category of vector spaces or vector superspaces. So superalgebra is just an algebra in the category of vector superspaces. What I've been doing is to consider algebras in other categories. Let's see. And perhaps there may be reasons to study algebras in other categories. That will be a generalization of superalgebras, or algebras and superalgebras. And so in other characteristics, at least these Verlinde categories that can be obtained in several ways are not equivalent to the category of vector superspaces. So what one gets using the semi-simplification process is an algebra in a different category. However, Berlin categories have a full subcategory, which is equivalent to the category of vector superspaces. So depending on the automorphism, if you are lucky and you have an order 7 automorphism of an algebra over a field of characteristic 7, where the Jordan blocks that appear are very particular, then you may get a superalgebra. And this is actually what Cannon did in characteristic 5, because it seems that, well, essentially, apart from characteristic 2, most new simple contragradient Lie superalgebras are the superalgebras that appear in the extended Freudenthal magic square that I got with Isabel Cunha, and a few exceptions. And one is the exception I mentioned about in characteristic 5. So Cannon tried to get all these new simple Lie superalgebras in characteristic 3 or 5 using this question. So for him, the characteristic 5 was more difficult. So in characteristic 5, he had to find a nilpotent derivation with extra properties in order to construct the algebra. But still, there are things to do, yes.
Thank you.
Okay, are there any more questions? Okay, then can we thank Alberto for a very interesting talk? So thank you.
Thank you very much.
Bye-bye, Alberto.